Recording is gone now. And okay, I'm going to get started. I'm going to want to talk a little bit for as we were speaking about. I'm going to talk a little bit about the document which represents the test and then for the first half, and then I'm going to talk about the project a bit more for the second half. So we cover, a couple of people's different options here.
So if you're not, like I'm doing the exam.
Okay, let's do that right now. Since you two are doing the exam, let's do that first, and then I'll move on to the project, okay?
If I'm not doing the project, then I don't need to stay for the other time?
You don't need to stay at all. This is all voluntary.
I'm going to walk out in the middle.
Yeah, this is all voluntary. Anytime I have a review session like this, it's voluntary, right? So you can come, leave anytime you want, stay, yes.
For the exam, we can always go back.
Okay, I'll explain that. I'll explain that right now. Let me just get this set up so we can look at this. Okay, so here's the exam. The exam consists of 3 problems. I even made it a little easier for you. I even told you what part of the course the 3 problems represented. The first one's analysis of variance, right? So and how do I know it's analysis of variance? Well, I'm looking at data for 4 different groups. In other words, we have 2 variables here. One is the department, the major, and the other is some numerical variable, which I guess is a test score, right? And so we're going to be comparing the average score for education majors, for business majors, for behavioral science majors, for fine arts majors. Now, if I were only going to compare the average score for 2 majors, right, education and business, I would do a t-test. Right, and the t-test would be the factor would be the major, and the numerical variable would be my average, is what I would be doing. Now the problem is I have 4 groups here, not 2 groups. So in that case, I do analysis of variance instead. Okay, so that's why I know that this is analysis of variance immediately. The next problem, and I'll come back to that in a second. The next problem is chi-square and odds ratio. Okay, and what kind of data do I have there? Well, you don't see the data here, but it's a file called stenosis.sav, something like stenosis.sav. And what's in there? In that file, there are 3 columns. There are 3 things in there. There's gender, male or female, for each person in the study. There is whether or not they're a smoker or not a smoker, and the third is whether or not they have stenosis. That's a heart condition, basically. I don't know if it's a narrowing of the arteries or a valve condition. I guess it could be either, right? So at any rate, they have a problem, right? Yes or no. So all 3 of those are categorical variables: male or female, smoker or non-smoker, and the third one was stenosis, yes or no. That's the outcome. So I could do a couple of things there. One thing I could do is I could try to see, well, are males or females, is there an association between gender and smoking? Are women more likely to, and like that's a little bit more generally, a little bit more specifically, are women more likely to smoke than men? Are men more likely to smoke than women? That's one thing I could do. I could also do gender and stenosis. Are males or women in this study more likely to have stenosis? I could also do smokers. Are smokers more likely to have stenosis than non-smokers? Right. So you could do a few different things here. In this case, I'm asking you to just look at the variables smoking and stenosis, just that pair. So what is that? Smoking is yes or no. Stenosis is yes or no. So there are 2 categorical variables with two values. So it's a 2x2 table, right, that we're going to create for chi-square. That's what you would do with something like this. You would create a 2x2 table, right? So I put this in here: gender and stenosis not required, and so on. Just that one setup, right? So, and it's going to ask you to do various things, but create a crosstabs table. Now you may notice that it says here, paste a table in here. Now this document, this Word document, the first problem, the second problem, it asks you the various questions. They're really steps in the process. Rather than just ask you to just do it all yourself, I broke it up into steps. Okay, so now you're not just going to have this document. I'm also going to be posting it's a test input page, like a regular homework, where you would go in there and for problem 1A, for problem one, the first part, calculate the mean test performance for each group. I would ask you to type that in there, right? And then for the next part, what test will you perform? I might give you a multiple choice or something like that. And for the next one, well, no. So you would use this document to do your work, but then you would put the answers into that. That's not available yet. Now, what do you do with this document when you're done? Right. So, for instance, it says paste the chart in here. You don't really need to upload this document. You can just answer those things. The reason why it would be nice for you to also upload this document besides answer the questions is, yeah, you could paste stuff in here, type stuff in here. I want you to show me your work, because what that means is, let's say on a lot of the homework assignments, a lot of the other stuff, the other exams, if you wrote in if the answer was 2.7 and you made a division error and you wrote down 3.6, you were wrong on that answer. But if I can see the process was right, you just made a minor calculation error, I can give you part credit. So if you upload this, if you answer the questions and you upload this, I can go back and look at how you got to that point. Exactly right. So it's a good thing. It would be good if you do that. You don't have to. You can just answer. If you have the confidence to do it, you can just answer it. Right. So yes. Okay. Well, let's talk about that. What is the null hypothesis for analysis of variance? Remember, it's like, what's the null hypothesis for the t-test? Mu1 is equal to mu2, whatever you would perhaps name the groups, right, for instance, right, male or female, for instance, mu not x bar, but mu1 equals mu2, right? But this, you're comparing more than two means, right? So what would the null hypothesis be? Mu1 is equal to mu2 is equal to mu3. In this case, you might call it mu ed equals mu bm equals mu bs equals mu, so on, right? Right, they're equal. And what's the alternative hypothesis? That they're not equal. That at least two of them are different. That they're not all equal, right? That's your null hypothesis, and that's what you're trying to prove. And you do it when you remember analysis of variance. You would then do it in SPSS. And first thing you would do is the analysis of variance. And if you got a significant result, the p-value or significance less than 0.05, what would you do then? You would say, gee, now the next thing I want to know is which of the two groups are really different. So you would do the post hoc tests and see which one's the significance on the post hoc test. Is education and business really different? Or is education and behavioral science? You would look at the results of the post hoc test to see which ones are different, right? Okay, so and then you would so on and so forth. So the p-value here, for instance, is the significance for the ANOVA, and then you would do your post hoc test, and it doesn't ask you for the p-value, just asks you which of the groups are different. And you could say, whichever ones they are. Could be education and behavioral science majors are different, education and fine arts majors are different, but business majors and fine art majors didn't have a difference. What this difference was not significant, so you wouldn't list them. Right, so you list all the ones where the significance came out to be less than 0.05. So let's take a look at the second one, chi-square. Well, with chi-square, those are categorical variables, right? So what you have to do is you have to create that crosstab table. It's the rows and the columns. So you tell me, smoking and stenosis, which one? We put the exposure in the rows and the outcome in the columns. Which one do you think is the exposure? Smoking, I'd say the same thing, right? Smoking causes stenosis, not stenosis causes smoking, right? So you create that variable, move those variables, and the outcome in the columns, right? And then you would calculate your chi-square value. Okay, the other thing you might want to calculate is your odds ratio. And I think it asks you for your odds ratio. And it asks you for the null hypothesis for the chi-square and the null hypothesis for the odds ratio. I'm going to ask you now, what's the null hypothesis for odds ratio? If there's no association between smoking and stenosis, what would you expect the odds ratio to be equal to? 1, right. So that OR equals 1 is your null hypothesis, right? Well, for chi-square, you probably have to form a word word null hypothesis, right? There's no association, or alternative, there is an association. But you can do that. You can figure that out, I think. Okay, now the last one is correlation and regression. So what are we asking you to do there? We're asking you if now what do we have here? We have two numerical variables, right? So the first thing we probably want to do if there's an association with a numerical variable is what it asks you for first. Create a scatter plot, right? And you do that, you go up to graph, legacy dialog, scatter plot, and then just move either whatever variables in there, and so on. And then you would look at the scatter plot, paste it in there, and you would say, "Gee, it looks like there's an association there." I hope there is, because I think I set it up so that there is. I hope so, right? But then now that you've done that, you would do the Pearson. You calculate the Pearson's correlation coefficient. Okay, and what's a good correlation? Closer to 1 or -1 it is, the better the correlation is, right? And if it's 0, yeah, 0.5, even 0.2 is a correlation. May not be a great correlation, but it's a correlation. And there is also significance there that tells you whether or not you can say that it's really different than 0, no correlation. So that's got to be less than 0.05 also, right? And then you can go to the next step and you can do a regression, where in the regression you actually measure what the association between these two variables is. You create a formula for them, right? And how do you do that? You go to analysis, regression, linear regression, and in the boxes you have to put in the independent variable and the dependent variable. So in this case, for age and blood sugar, the independent variable is the one that causes the dependent variable to change, right? So age would be the independent variable, right? We all agree on that? Mm-hmm. And blood sugar would be the dependent variable. So you would do it in a regression, and the regression would give you a bunch of numbers. We saw the tables. One of the numbers is R squared. You guys remember what R squared stands for? What is R squared? Remember, R gives you an idea of how good a correlation it is. The proportion, the amount of the variability in the dependent variable, in the blood sugar, that can be attributed to the independent variable. In other words, if R squared is 50% or 0.5, then you would say 50% of the variability, the change in blood sugar, can be attributed to somebody's age. 50% could be something else. Because, exactly. And 10% could be attributed to if they drank a lot of Coke today. 10% could be how much exercise they get. 10% could be, but whatever it is, R squared is, that's what portion of the variability in blood sugar. Yeah, it is what R squared represents, right? Okay, so but then you also have another table that gives you the y-axis and the slope for your equation, right? Now, once you have that equation, right? Once you have that equation, y is equal to, the y-intercept plus beta x, the slope times x, right? Once you create that equation, now instead of y, you can say instead, blood sugar is equal to some number plus the slope times the age, right? So now I could say to you, let's say I bring in a 52-year-old man here. I think I said 52, would say 40-year-old man. And I ask you, what do you think his blood sugar is going to be? You can plug the age into that and predict his blood sugar, right? For whatever accuracy you might get. Now, there's a lot of ways that you would use this kind of a hokey version of this, right, for our exercise, right? But for our understanding of how to go through the process. But in addition to that, you can use it predictively, and there's other ways to use this. There's logistic regression, there's multiple regression. Multiple regression, you could actually put in many factors, but we're not going to worry about that from now. Just that we went over it just in terms of like that it exists. I think I did a quick example of it, at the very end of the session. And we can add in other variables there. So there's other slopes and x's that are in that formula. The formula gets bigger, but we're not going to worry about that. We're just going to
predict it, like you're saying, you can predict in whatever years that's up. like how do you do that prediction?
By filling in the values that you know. So, for instance, if you know how much they exercise, you know how much sugar they eat, consume a day, you know, those might be the other variables. So you would have a formula where you can plug in that the blood sugar is equal to some slope times the age plus some slope times the exercise value plus some slope times the sugar consumption value or something like that. But we're not going to worry. That's multiple regression. We're not for this
just
exam.
In general, when you just have two, not multiple.
Yeah.
Like in other words, if you got that number when you multiply the age
to
this
alpha
plus beta times the age, that helps you predict in the future.
Yeah, exactly. So in other words, instead of taking somebody's, the idea here is that let's say that it was a very expensive test to do a blood sugar, right? Well, if you needed to estimate a person's blood sugar when you were admitting them or something like that, and you didn't have time to do the test, you could say, oh, let me plug it into this formula. And now, based on his age, which I know can get easily, I'll assume that his blood sugar is around this much. None of this is really legit. But, right. Okay. So it's a mechanism for predicting. And why would you want that?
From years from now, like in 10 years from now, in other words, we can know what his blood sugar is going to be.
Oh, there you go. That's a possibility, right? And in fact, the last question on here asks you that if there's for a difference in age of 10 years, how much of a change in blood sugar would you expect? How much would you expect the blood sugar to go up?
I don't know how to figure that out.
Well, you could figure it out for a 40-year-old man and for a 50-year-old, right? Or you could just say the slope. Look at the slope and figure it out in your head what it is as well. Okay? So I'll leave that up to you guys to figure it out. Yeah, can you get that from the chart that comes out with the regression? Remember, there's a constant and a slope. Right? So you can go back over some of the previous videos and stuff like that. Okay. So I mean that's really what it is. That's a pretty easy test. I don't, and now I've filled you in on a lot of it also. I haven't actually done the problems, but I think I've kind of steered you in the right direction. Okay, and hopefully I want to make sure that other people get a chance to see this so it's fair. So I'll get to post this and I'll try and emphasize that they see it. Let me just go online here and make sure that if there's any questions here. Hey guys online, who's online now? Let me first of all go in here and see who is here now. If I can find it here. Where is it? Oh, here it is. Oh, take care, guys. Now I'm going to talk to an empty room again. So it's a little freaky, So that's not a problem. I have some people on. I have a couple of people online, so I'm sure they'll be with me for a little while. Take care, guys.
We can always come back to the exam, right?
You can come back. You have the document. You can work on that anytime you want. Obviously, when I put up within the next day or two, I'll put up the answer sheet that you can fill in. You can start working on that, putting the answers in. It won't give you any feedback. You can save your work so you don't have to keep putting it in over and over again. But don't hit submit until you're ready to submit it. Okay? And if by some mistake something happens and you accidentally submit it, just email. We'll figure something out. Okay, take care. Good luck. Okay, take care. Bye. Okay, so now that I don't want to give any more of the farm away here, so hopefully that'll help out you guys that are struggling a little bit with how to deal with this homework. This exam 3 option. Okay, so let me put this away for now. And next, I want to spend the next half hour or so talking about actually doing some of these analyses using SPSS. Okay, and particularly where it involves the project. Okay, so Mavis, since you're online right now, did you have a specific question that you had? Can you hear me? Okay. Oh, okay, good. Okay, good. All right, good. And what I'm going to do is I am now going to go through the saved data. Last session last review session, I know there was an issue with an echo because there was a microphone on somewhere that I didn't notice, so I didn't have the opportunity to mute it. But what I'm going to do now is I'm going to go and I'm going to open up the Community Health Survey, the simplified data set, and I'm going to demonstrate how to code the data so that and what kind of format all of the data is in, so you can make a judgment as to what kind of analysis that you need to do. Okay, so Mavis, which variables are you working with? In the meantime, I'll open SPSS. Open data. Okay. And I'm going to open up this reduced data set. Is that the one that I created, or is that the that's the one I created during the last session. I'm not going to work with that. I'm going to work with the one we gave you originally. Gender and flu shot. Okay, good. Okay, so let's see if that's in that data set. Open data, and let's see, simplified flu data. Okay, so let's see what we have here. We have demographics, we have borough, we have new race, we have insured, uninsured, gender, sex. We have gender in here too, and we also have, let's see, flu shot, yes or no. Okay, so now the only problem we have here is that normally I could go up here to view and say value labels, turn them on and off, and these numbers would change into what those numbers represent, like yes or no, they got a flu shot, male or female for gender, and so on and so forth. But they're not there because this data set is not at this point is not completely coded. Okay, so I'm going to go ahead and code this data set so we can see how to do that. Then I'm going to upload it to Blackboard so that it's available to everyone to use for their projects if they wish to use this particular data set. So I'm going to close that one. So in order to code this, I need the code book. Okay, so let's see. I think it's in here. Here's the code book. So this code book represents all of the variables that are in this data set. It describes all of the variables that are in this data set. So I'm going to, let's see, we don't need those drawings. Okay, and we don't need this for now, so I'm going to get rid of that. Okay, so I'll start with the first one, demog1. What is demog1? I'm going to go to the variable view. Demog1 looks like age, and in fact, it really is age. If I do a search in here, demog1. Actually, I think I wasn't able to find it. Yeah, demog1. If you look, if demographics 1. How about if I just do this, age? Now, it's going to take me too long to find it. You're going to have to take my word for it that demog1 is a numeric variable and it represents a person's age. Okay, SPSS already recognizes it as being scalar. Okay, now the label that's here says, what is your age? So we know that that's the question that was asked. So now we know for sure that it's the numerical variable and it represents age. I'm going to simplify this, and I'm going to say, I'm going to type in here subjects age. So now that label will be used instead of that question. Okay, so I'm going to go to the next variable. The next variable is borough. Let me hang on just a second. The lights went out in here because there's nobody sitting out in the classroom there. So I had to move out in front of the lectern to get it to see me. Okay, so let's take a look at borough. Well, I'm going to look in borough here. I'm going to search for borough. Okay, and the variable borough represents the borough of residence. And look, it tells us what 1 represents, 2 represents, 3 represents, and so on. So obviously there's 5 values there. So in borough, I'm gonna just shorten this to borough of residence. Just make it a little easier when we make charts and stuff like that. And then, since it's a categorical variable, see, nominal or categorical variable, same thing. I can give it values. I can assign it those values. So, for instance, for the value 1, I can say that the label represents the Bronx. 2 represents Brooklyn. 3 represents Manhattan. 4 represents Queens. 5 represents Staten Island. And that's it. Those are all the variables that are there. I'm going to click OK. Just to show you what's happened now, if I go back to the data view, okay, the variable names stay the same because only the labels have changed. In other words, demog 1, we didn't change the variable name, only the label. That instead of that question, it says now subject's age and so on and so forth. And borough was borough as before. But you notice now for the categorical variable borough, we can see the actual what that value represents. You can go up here to view and toggle that on and off if you want to see the numbers. Notice that first one is this subject. The first one is from Manhattan. If I go back to value labels, you can see that, yeah, indeed 3 represents Manhattan. So I'm going to go back to the variable view. And next, I'm going to take a look at race and ethnicity of the person. Okay, so I'm just going to change that to race and ethnicity. And it's called new race. The value that's the variable name is called new race. I'm going to see if I can't find that here. Okay, new race represents 5 groups: white, non-Hispanic, black, non-Hispanic, Hispanic, Asian, Pacific Islander, and non-Hispanic, and other non-Hispanic. So I'm going to code this now with those values. Okay, and in fact, it is nominal. Check that. So I'm going to go in here and I'm going to recode these values just like I did before. And I'm going to move this out of the way so I can see it. Okay, so 1 represents white. I'm going to keep it simple. 2 represents black. 3 represents Hispanic. 4 represents Asian Pacific Islander. And 5 represents other. Oops, I didn't put a 5. I put 4 in there. 5 represents non-Hispanic. Okay, good. All right, so now that's coded. If I go back to the data view, I'll see that that's coded as well. Next one is neighborhood poverty. Okay, so right now that looks like a nominal variable. Let's see what the data looks like for that 4th column. Neighborhood poverty. Okay, it looks like it's categorical data. It's not like percentage of the of that neighborhood that is below the poverty level. We would see percentages or proportions there. In this case, it's a category. So let's look up that category. Neighborhood poverty group 4. See if I can find it. They didn't find it. I must have misspelled it. Oh, POV instead of being spelled out. Oh, I still missed it. Nay. Nay. POV group 4. Ah, there we go. Bingo. Here's a neighborhood poverty group, and 1 represents less than 10% is below the poverty level, 2 represents less than 20%. 3 represents less than 30%. 4 represents less than 100%. Very high level of poverty. Oh, greater than 10%, greater than 30%, and so on and a very high level. This is really greater than 30%. Okay, so let's fill that in now. 1, 2, 3, and 4 for 10 through 30. Okay, so now let's go to my data view, variable view. Okay, neighborhood poverty group based on zip code. Okay, I'm simplifying this a bit. Okay, 1 represents less than 10% below poverty. Okay, I'm going to copy that, make it easier for myself. 2 represents less than 20% below poverty. 3 represents less than 30% below poverty level, and 4 represents very high level of poverty. Okay, any comments on that so far? Good, you did the coding for yourself as well. Good, excellent. So let me finish up the coding here. So insured, that's likely to be a yes or a no, I think, right? So let's take a look at that column. So that's all 1s and 2s, it looks like. And insure 5 is a bunch, it goes 1 through 5. So I'm thinking that's type of insurance. So let's take a look at our code book. Insured. Okay, and here's insured, and 1 represents yes, and 2 represents no. Okay, let me again get the light back on here. Okay, let's go back to our SPSS file, and let's see. Variable view, insured or uninsured. So I'm going to copy that down from there. And I'm going to say 1 represents insured, and 2 represents uninsured. And I'm going to click OK. Okay, and what type of health insurance do you have? Well, that's the next variable here. I think insured, what was that now? The variable name was insure 5. I see it. Here's insure 5. Here we go. It's 5 values that it has. Okay, so our 5 values type of health insurance. 1 is private. 2 is Medicare. 3 is Medicaid. 4 is others. Other. And 5 is uninsured for that group. Okay, so we're getting there. Received a flu shot or spray in the past 12 months. Okay, that's pretty straightforward enough. I won't change the label on that. And the variable is flu vaccines. Flu vaccine shot. And there it is. 1 is yes and 2 is no. 1 is yes and 2 is no. Add that. Okay. And let's see, gender, sex, gender, that's also going to be 2 values. Okay, this might be a little bit hard to find because of the number of variables that have similar names. I wonder if I do it with a space in it, sex and a space, if that doesn't help. How about this? How about, yeah, that's not going to work. I don't see it there. Okay, nope, not quite. Sexual behavior, sex, there it is. 1 is male, 2 is female. 1 is male, and 2 is female. Okay, and nativity, born inside the United States or born outside the United States? Okay, that's what that stands for. Nativity. Oh, didn't find it. Try again. Did I spell it right? Oh, no, it's US born is the variable. And let's see, 1 is US born and 2 is foreign born. 1 is US born, and 2 is foreign born. Yeah, if I tried male or female, I probably would have brought it up a lot quicker. Thanks. Born. Okay, and finally, the last one is number of children under 18 years living in the household. Okay, so children 13. Now, that could be a numerical variable, the actual count of children, or it could be a categorical variable. And groups like no children, 1 through 5, 6 through 10, or sadly 11 through 20, or something like that. So what is that? Oh, yeah, it is a category, right? It isn't really a category up until you get to 5, but it was really you're going to have to work with this as categorical, unfortunately. Okay, because 1 is none, and 2 is 1, so it won't make any sense otherwise. Okay, so starting with 1, we got none, 1, 2, 3, 4, more than 3. So let me get that in here. Number of children under 18 years, okay. 1 represents none. 2 represents 1. 3 represents 2. 4 represents 3. I think. Let me just check. 4 represents 3. 5 represents more than 3. Okay. And 5 represents more than 3. And we're okay there. And that's the last variable that we're going to code. Okay, I'm going to go back to the data view so we can actually see this. Let me minimize this. Take a look at our data view. And now we can see this data fully described with the various values that are involved here. I'm going to save this. Save as. I'm going to save it as an SPSS file. I'm going to call it flu data coded. I'm going to put that in caps so it's easy to notice. How's that? Okay, and it's going to go into that same folder. And I'm going to upload this to Blackboard so it's available to you guys to use if you would like to. Okay, so now let's take a look at these various variables. So let's say that I wanted to examine what the average age of males and females, or how about US born and foreign born, right? 2 values here, and I have all their ages. Let's say I wanted to compare whether or not the average age of US born people in New York in the survey is equal to the average age of foreign-born individuals in this survey. Maybe foreign-born individuals in this survey are younger than U.S.-born, and that we might want to consider that when we look at this other data as well. Keep in mind that they might be a younger population, or maybe an older population. Who knows? Let's take a look and see what it is. So now, if I wanted to evaluate that, I could go into Analyze, Descriptive Statistics, Explore. I could say, let's move the nativity, let's move the average age, the subject's age, into the dependence list, and let's break it up by the nativity, by U.S.-born and foreign-born. And we can say, okay, an output window comes up, and it will tell us that the average age for U.S.-born is 50, and the average age for foreign-born is 48. So it does seem like there's a bit of a difference, right? We don't know if it's a statistically significant difference yet, but it looks like native-born are smaller. So let's go back now and take another look at this. Let's analyze this. Now, we're looking at a categorical variable with two values, U.S.-born and foreign-born, and we want to compare whether or not their means are different for a numerical variable like age. We use a t-test. Two values within that variable, we use a t-test. Analyze, compare means, independent samples t-test. I move in my numerical variable, and then I move in my grouping variable, my nativity. Now, it's going to ask me to define the groups. So I know they happen to be 1 and 2. I happen to remember that. So I have to put that in there. And then I'm going to click OK. And SPSS does a side-by-side blocks plot for us, and we can see that the median age for foreign-born is lower than for U.S.-born. Both of them have this one have the bottom feather at about 18, but that makes sense because the limit of the bottom age on this study was 18 years old. So that does make sense. Okay, what about our t-test? Well, our t-test is over here. Now, this is our t-test. This is our significance test for whether or not the variability is equal or different. Okay, in this case, in this case, whichever row that we pick, we're going to wind up with similar answers anyway. However, because the significance is less than 0.05 for the test of equality of variances, we use the bottom row. But you want to know something? You probably wouldn't be in terrible shape if you used either one of them. Okay, so I'm going to look at the bottom row. Equal variance is not assumed. The t-test is 4.45, 4.46, and the p-value, the significance, is less than 0.05. It's 0.000 or less than. It's actually less than 0.001 is really what that represents, right? So what would be the null hypothesis of this? Mu age for U.S.-born is equal to mu age for foreign-born. The alternative hypothesis would be mu age for U.S.-born does not equal mu age for foreign-born. Well, that's pretty good. That seemed pretty straightforward. Now, what if I wanted to compare the average age, for instance, for the different ethnic groups that are within this study? Well, now, when I look at different ethnic groups, if I compare their means, let's compare means.
Professor?
Yes.
How you doing?
Good. I'm not talking to myself. I'm online.
Oh, okay.
In case you were concerned.
Yes, I was.
Okay.
Because they see you on camera talking and they think you're probably. However,
yes.
how long will you be here?
I'm going to be here about another 15 minutes, 10, 15 minutes.
Something going on here at 6.
I'll be out of here well before that.
Perfect. Thank you.
No problem. Anytime. Okay, so at any rate, they're seeing me on camera talking to the computer all by myself, so they think I'm nuts. Okay, that's your fault because you didn't come in here. Okay, so at any rate, if they put me away, it's going to be your fault. Okay, so at any rate, now, independent samples t-tests. Okay, except this time, let's see. First of all, let's get descriptive statistics first. Descriptive statistics explore, and this time, instead of nativity, I want to look at the average ages by ethnicity. Okay, and that's by race and ethnic group. I'm going to move that into the factor list instead and click OK. And it will show us the average age for whites, for blacks, for Hispanic, for Asian Pacific Islanders that look like the youngest, they're right there, maybe not, yeah, and other non-Hispanic, and so on and so forth. So we got the average ages. We get a look at the average ages. We also get a box plot where we can see the distribution of ages for these different ethnic groups. Now, let's say I want to actually compare the means of these different ethnic groups, see if there's a statistically significant difference. Well, the problem now is that if there were only 2 of them, I could do a t-test. But now that there's 5 of them, I can't. I'd have to do multiple t-tests. And we know that there's a lot of problems with that. So instead, I do an analysis of variance. So I'm going to go up here and say analyze, compare means, because we are still comparing means, analysis of variance. I move the subject's age into the dependents list, and just like before, I move the race and ethnicity into the factor box. Okay, so I'm going to click OK. SPSS is going to compare these. What's my null hypothesis going to be here? Well, my null hypothesis is that there's no difference between the means, right? So mu age of blacks is equal to mu age of whites is equal to mu age of Hispanics is equal to mu age of Asian Pacific Islanders, et cetera, et cetera. And what's our alternative hypothesis? Is that at least 2 of those means are different. Okay, so now we want to prove that. So now we have to run an analysis of variance, and in fact, our analysis of variance indicates that that it would be very unusual to get this big a analysis of variance, analysis of variance statistics F, get that big of analysis of variance, and for not to have any of these means be different. In other words, there's a very low chance, less than 0.05% chance that we would be wrong to reject our null hypothesis that all the means are equal. Okay, now that we know that, we want to examine which of these means are equal. And in order to do that, I have to do post hoc tests. I'm going to go in here, analyze, descriptive statistics, analyze, compare means, and over, go back to the same spot I was before, except this time I'm going to go into post hoc, and I'm going to say we want to do some post hoc after the fact tests, after the fact that we can reject the null hypothesis. If we couldn't reject the null hypothesis, we wouldn't do this. If that significance were greater than 0.05, I wouldn't do this, but it is, so I'm going to do it. I'm going to use Bonferroni, which is a relatively conservative version of these post hoc tests. I'm going to click that. I'm going to say OK, and this time it's going to do exactly the same thing, except this time it's also going to show me all of the comparisons of these different groups to each other. So white versus black, the significance is less than 0.05. So I can reject the null hypothesis is that average age for whites is the same as blacks, or whites and Hispanics, and so on and so forth. The only ones that don't look that there's a significant difference is between blacks and non-Hispanic and other non-Hispanics, or Hispanics and other non-Hispanics. All the rest, and Hispanics and Asian Pacific Islanders, right? So you could actually list all the different groups for which there are that the significance is different, or you might just want to take a look at this and say, well, the group I'm most interested in is, say, white and Asian Pacific Islander. White and Asian Pacific Islander is a significant difference. I can reject the null hypothesis for that. But you can see SPSS actually repeats these several times. That's why, white and black is also repeated black and white, which is exactly the same result here for significance. Okay, so that's how we would do that. Now, let's say I had 2 numerical variances. I can't do that here, can I? Because I only have 1 numerical variable in this data set. So I'm going to open up a different data set. Open, other, data. And I'm going to go up to the desktop and see what I might have here. Okay. And I don't want to use that one because that's the one that's on the test. Okay, so how about this? Trees. Okay, here's one. Here's a good one. Trees. Okay, here's a test that shows the. I'm only going to look at these first 2 variables: tree height and tree diameter. It's hard for me to measure the height of a tree if I don't have a transit and a lot of a very long tape measure and so on and so forth. But I can measure the trunk diameter pretty easily. So I want to know, since I got to go out and survey trees, can I predict the height of a tree based on its diameter? Okay. Oh, well, what am I looking for here? Well, my null hypothesis is that there's an association between tree diameter and tree height. Sounds like it makes sense, right? Okay, so now I want to examine that relationship. So the first thing I might want to do is, since they're both numerical variables, I might want to take a look at them on a scatter chart. So I go into Graphs, Legacy Dialogues, Scatter Dot, and select Simple Scatter Dot. And then I fill in for the x-axis, I'm going to put in, for the y-axis, I'm going to put in tree height. And for the x-axis, I'm going to put in tree diameter. I'm going to click OK. Okay, let's see what that looks like. Wow, that looks like there's a relationship there, right? As it gets taller, the x-axis, as the diameter gets bigger, the x-axis, the height gets taller as well. Okay, so it looks to me like there's a significant relationship there. Okay, so now what I'm going to do now, actually I can click in here, double click in here, and I'll get a window, and if I go up to this line over here, which will actually produce a fit line, I'm going to click on it, and then all I have to do is close it. You can see that it creates a line which is the best fit for this. All of the squares of all of the different distances between the values in a line for each individual measurement are equal, add up to be equal on both sides of this line. Okay, it even creates our regression formula way ahead of time for us, right? And we're going to continue to go forward with this. But again, you kind of cheats. It's kind of a little bit of a cheat because we got that all the way up front, where we're really not going to get it till later on. So I'm going to close this. It'll stay here in the background version of it. Okay. So now I want to measure how strong a correlation is that. So I'm going to go up here to Analyze, Correlation, Bivariate. I'm going to move tree height and tree diameter into the variables. And I'm going to ask it to calculate the Pearson's correlation for me. Okay, and the Pearson's correlation is 0.886. Now, I'm going to leave it up to you. You might remember that a correlation of +1 or -1 is a very strong correlation. 0 means no correlation at all. So this looks like a strong correlation. And the probability that it's not 0 is this significance here, 0.003. It's less than 0.005. So I can say with a high level of certainty that this correlation is not 0. There is a correlation between these two sets of numbers, and in fact, it looks like it's a pretty good correlation. So now, let me walk around again and get the light on. Good. So now let's take a look at where we can go from there. Now I'm going to go to Analyze. I'm going to go to Regression Linear. And I'm going to do the same thing, except this time, SPSS wants to know which of these two variables is the predictor and which is the predicted. So the independent variable, the predictor, is the trunk diameter. That's the one that I'm going to use as a predictor value. Okay, and the dependent is the tree height. That's the one that I want to predict. Okay, so I'm going to go ahead and I'm going to click OK. It's going to calculate our correlation again. Indeed, here it is. Here's our correlation again, just as we did before. It's going to calculate R squared. R squared is equal to 0.785. It literally is R squared. Okay, so now what does that tell us? That tells us that 78.5% of the variability in tree height is predicted by the tree diameter. Okay, so that's really good. That 25% of the variability is from other factors, whatever they might be, the amount of sunlight it gets or something like that. But 78% a little more than 78% is due to the tree diameter. These numbers are probably not real. This is pretty optimistic, right? And down here, we can see those coefficients that were in our predictor formula. Okay, -1.3 is our y-intercept, and 4.541 is our slope. So if we go back to that formula, you'll see those same numbers in that formula, -1.31 plus 4.54 times x. So what our formula now allows us to do is predict that the tree height is equal to 1.31 plus 4.54 times the diameter of the tree in feet. So we can use this formula to attempt to predict the height of other trees. Okay, so in fact, if I told you that a tree diameter was 8 feet, you would just plug in 8 for the x, multiply 4.5 times x, comes out to 36, add it to 1.3, 37.3 feet is what your prediction would be for x. Okay, if for instance, I came across now this particular tree that we see here, for instance, is might be, looks like it's let's see, looks like it's about 9 feet, 8.5 feet in diameter, and the height of the tree is 48 feet, let's say, roughly, right? Now our line predicted that the height should have been around 42 feet, right? So we were off here by about 7 feet, right? So that is called a residual, or our error for this particular measurement. Okay, so you could actually, for the values you have here, you could actually calculate what the residuals are, what the error that in the individuals that we calculated here. The other thing that you can do is that you could say to yourself, 4.54 represents the slope. That means for every one value, every diameter, every foot of diameter that the tree increases, the height increases by 4.5 feet. That's what the slope represents, the change in y, the height in this case, over the change in x, the diameter of the tree. The other way you could do that is you could just simply say, well, what is the height at 0 feet, at 6 feet, and what is the height at 8 feet, or at 7 feet? And you can compare those two values on this line, how much you go up on the y-axis on this line, and that will also tell you the difference between those two values. 6 versus, at 6 feet in diameter, it looks like about 25 feet. At 7 feet in diameter, it looks like about 30 feet. So subtract the 30 feet from the 25 feet, it'd be roughly about 4.5, and that would represent the amount of difference that change in height would be, that change in diameter would be. If you wanted to examine the change between 6 and 12 feet, you could just literally see what y is here and what y is here, subtract one from the other, and you know that for 6 feet in diameter, 6 foot in diameter change, a change in diameter of 6 feet, you would have a change in height of the difference between the y value here and the y value here. Okay, so I need to give up this room now, and I think we have a pretty good start on this, and hopefully this will help you with doing the problems that are in the assignment if you want to, or by using this data set in order to facilitate your project, or if you're using any of the other variables, understanding that each variable type, the variable types determine which statistical test that you should use, whether it's analysis of variance, t-test, or chi-square, and so on and so forth. Okay, we didn't do chi-square here, unfortunately. You could do I'm going to do a real quick one. Analyze descriptive statistics, crosstabs, and I'm going to, oops, I can't do it in this one. I got to go back to my other window. Okay, and I'm going to compare, let's see, let's take a 2x2. Okay, let's say insured or uninsured versus gender, sex. So I want to see whether or not there's an association between gender and whether a person is insured or not. So analyze descriptive statistics, crosstabs. It's going to be a 2x2 table. The exposure is going to be gender. That's a yes or a no. The outcome is going to be insured. Yes or no, right? They're both categorical variables. That's why I'm using chi-square. I'm going to ask it to calculate the observed values and say the percentages by rows. And I'm going to also ask it to calculate chi-square and our risk. Risk is going to give you the odds ratio and the relative risk. I'm going to click OK. And very quickly, what do I wind up with here? Well, my chi-square value is 107 and with a significance of 0.000. So I can reject the null hypothesis that there's no association between gender and whether or not a person is insured. And further, here's my 2x2 table here. I can further say that the odds of the odds for let's see, males are insured at 78%, females are insured at 87%. So the odds that a person that a male is insured is about 55% of the odds of the likelihood of a male being insured. Okay, it would have been nice if we could have flipped them, but that's okay. So that gives you an idea of how we might use this. Hopefully that helps you out on the exam and on the project. I'll post this onto Blackboard for those guys that weren't here. So I wound up talking to myself and making the guard think I'm crazy. And I'll talk to you guys again. I'll see you guys. Those guys at Brick and Mortar, I'll see you on Monday. Hopefully we'll have some interesting projects going on Monday. And the rest of you guys, I'll see you online. Take care. Bye.